Right, good afternoon, everyone. So we will continue with our lecture. So we have a little bit residual chapter 4 yang tak sempat cover on last week. So I will cover today just a little bit, but the last part is also important because this last part we will address one kind of reaction that we have not yet covered in our design of reactors, which is if we have reversible reaction. Okay, so all this while when I teach you irreversible reaction. Maksudnya reaction tu only goes forward direction. But you also must remember that reaction also can occur reversible, meaning the reaction will occur forward and backwards. Okay, so we also have to address how it affects our reactor design if let's say you have reversible reaction, right? Okay, so if you want to understand what is actually reversible reaction means, okay, so let's say you have a reaction, let's say you put in your raw material, your A and B into the system, into the reactor. So what happens is the reaction will first occurs, okay, forward. So means A and B will react to form C and D. Okay, subsequently, it will also goes backward, meaning C and D can also react with one another to form back A and B. So it goes forward, backward, forward at certain time. But eventually, after certain period of time, depending on the reaction, it will achieve what we call as equilibrium. Okay, so what I mean by equilibrium, the rate of reaction is identically zero for all species, meaning minus RA equals to A. So why this happen is because at equilibrium, the concentration of A, B, C and D, they are at equilibrium with one another. Dia dah tak berubah, dah tak bertukar. Meaning unless you disturb the system, okay, the concentration dah remain constant, forward and backward. Okay, so it's only achieved at condition we call as equilibrium condition. And at this equilibrium condition, remember I told you at equilibrium condition, the concentration no longer changes, right? Okay, because of this, we can calculate one kind of constant we call as equilibrium constant. We have one constant, we call it as equilibrium constant, and this equilibrium constant we put it as Kc. Okay, sebelum ni you know K, reaction rate constant. Now we have another constant, we call it equilibrium constant. So equilibrium constant ni it only occurs if you have reversible reaction, one, and second, it must be reversible reaction at equilibrium. Okay, sebelum equilibrium is not valid, you can only calculate Kc at equilibrium. Maksudnya, when you calculate at equilibrium, the concentration, it will be based on the concentration of your reactant and product, and this concentration must be at equilibrium. Kamu tak boleh kira Kc menggunakan kepekatan sebelum tindak balas tu mencapai equilibrium. It must be at the moment when they have already achieved equilibrium. So Kc is actually the ratio of reaction rate constant K forward direction over reaction rate constant of the backward direction K minus. That's why you have K, you have K minus. K into denote to represent the forward direction. K minus is to represent the backward direction. So kamu kena faham nilai dia adalah berbeza sebab walaupun dia reactant dan produk yang daripada satu tindak balas yang sama, tapi forward and backward directions are considered two different direction. So in terms of concentration, this equals to, okay, the top part, Kc equals to the top concentration of C at equilibrium. Sebab tu ada CCE. Dia mesti concentration of C pada equilibrium. Power C. Power C ni lah power dia punya stoichiometric coefficient dia. So katakan yang tindak balas ni 1A, 1B, 1C dan D. So it will be concentration of C at equilibrium power of 1. Katakanlah kalau stoichiometric coefficient dia adalah 1. Then, if you have two products, so it's also multiply with concentration of D. Abdul Karim tutup mic ke kamu nak tanya soalan? Ush. Sekejap, saya mute kan. Tak boleh mute pula. Alright, thank you. Okay, so concentration of D at equilibrium, power stoichiometric coefficient as well. Over, okay, concentration of all of your reactants. Dalam kes ni katakan ada 2 reactant. So it must be per concentration of A at equilibrium, power of A, stoichiometric coefficient, multiplied with concentration of B at equilibrium, power stoichiometric coefficient. So naturally, this equation to find Kc is not fixed because you know, right? We have different reaction, will have different kind of product, different types of reactant. You may have 2 reactant, you may have 1 product, you may have 2 reactant, 2 product, 1 reactant, 2 product, 2 reactant, 1 product, so on and so forth. Tapi dia punya konsep Kc will be equal to concentration of all of your product species at equilibrium, power stoichiometric coefficient over concentration of all your reactants at equilibrium multiply with power of your stoichiometric coefficient. And it must be calculated at equilibrium. Dia tak boleh sebelum equilibrium. Okay, so for example, okay, you must then understand pula, okay, bila kita nak calculate concentration ni, tadi kan saya katakan ada CB, CAE lah, CBE lah, CCE lah, CDE lah. Kalau kamu ingat sebelum ni, kita pernah belajar kan nak cari CA, CB, CC, CD. So CA, CB, CD tu adalah concentration for irreversible reaction. Ataupun kalau reversible pun ada, tapi itu adalah concentration before dia achieve equilibrium. Selepas equilibrium, dia dah tak berubah, dia akan ada E. Sebab tu kita akan ada E. Sebab itu menandakan its concentration after equilibrium. So the same concept, when you want to measure the concentration, kita akan selalu measure in the form of CA0 dan X, right? Contohnya CA equals to CA0 in bracket 1 minus X. So the same, if I want to calculate CAE, CBE, CCE, CDE in the form of CA0, tetapi sekarang dah bukan X, dia jadi XE, meaning conversion at equilibrium. Naturally lah kan, kalau saya kira concentration sebelum equilibrium, dia akan menggunakan CA0 dan X. Pada equilibrium, dia akan menjadi CA0 dan XE. Okay, so same concept, we have to derive back CAE, CBE, CCE, CDE. But you also must remember, so this is the hardest part about reaction. Concentration, if we want to express, ada pula lain. Kita ada gas phase, kita ada liquid phase kan. Kita nak express concentration tu dah berlainan. If I have flow reactor, dan kalau saya ada gas phase ataupun liquid phase untuk flow reactor. Kalau batch tak apa. Kalau batch konsep dia liquid atau gas, dia punya express of the concentration is still the same. Just that for flow reactor gas, concentration dia kita dah express differently sebab yang jangan lupa we have the down part 1 plus epsilon XE kalau kamu ingat, dan kalau ada pressure drop kita kena address juga P per P0. So this is the hardest part lah, kamu kena somewhat understand, okay, macam mana kita nak express benda tu kalau kita ada reversible flow. Reversible flow liquid, reversible flow gas, reversible batch reactor. So now this slide explains how we express CB. Let's say you have CBE, you have CAE, kita nak express dalam bentuk CA0 dan XE. So you can see in this example, because the reaction is 1A react with 1B, right? 1A reversible to produce 1B and then it goes forward backward. So the Kc will be the concentration of your product. But of course, bila saya cakap produk tu maksud saya spesies yang dibelah kanan. Okay, sebab bila reversible, by right bila reversible, dua-dua tu raw material, dua-dua tu pun produk kan, sebab it goes forward, backward. Bila it goes forward, reactant on the left, the product on the right. Kalau backward, sekarang reactant on the right, product on the left, right? Tapi kita dah selalu biasa dengan irreversible, kita selalu kata tindak balas dia yang kanan adalah reactant, yang kiri reactant, yang kanan product. Okay, so I also somewhat still use the concept. So the Kc for this reaction, it will be concentration of B sebab kita yang dibelah kanan tu akan menjadi kita punya pengatas. So concentration of B at equilibrium, power of B per concentration of A at equilibrium, stoichiometric coefficient A. So you can see this is, let's say I have 1A, 1B. So, A, and B. Okay, A dengan stoichiometric coefficient tu tak sure lagi kan. It can be 1, 2. We do not know yet. Right. So if let's say pula kita ada case di mana kita ada 2 on the left, 2 on the right. So A, B, C, D. So kamu kena ingat macam mana kita nak express balik. Sebab tadi case tadi saya hanya perlu untuk express A dan B. Sebab A is the reactant, B is the product. But the case kalau saya ada dua pula reactant, dua pula product. Okay, so how do I express back the concentration to find the Kc? So sama konsep. Kita kena tahu how to express the concentration when they are reactant or when they are product in order for us to express Kc, right? So again, at this stage, if you find this a bit difficult, I can understand, but later on we will discuss questions so that we can directly focus how do we apply this in calculation. Essentially, kenapa kita kena tahu Kc? Okay, kenapa kita kena tahu calculate Kc? Sebab nanti dalam rate law kita tu dah ada Kc. Kamu ingat kalau reversible reaction, dia dah ada rate law dia yang berlainan. So dalam rate law tu ada nilai Kc. So sometimes we might need to find the Kc first, or sometimes from the Kc yang kita tahu, kita kena cari let's say conversion at equilibrium. Kita boleh guna Kc untuk mencari Xe, so on and so forth. So later I will explain why we need to know that. So at this stage, we just understand how to find the Kc, right? Okay, so example case macam ni lah. So example case macam ni, let's say now you have chemical equation as following. 2A reversible reaction to produce B and C. So let's say kita nak express Kc dalam bentuk Ca0 dan Xe. So you may ask, kenapa setiap kita kena buat macam ni? Sebab bila kita design reactor, we cannot be able to measure CAE, CBE, CCE, CDE. Kalau bayangkan satu reaktor tu, you have mixture of compound. It's impossible for you to separate. Kena pasti berapa concentration A, concentration B, concentration C, concentration D. So what we do is, as long as you know Ca0, you know Xe. Dalam kes ni kita tahu Xe, Ca0 kita dah boleh tahu CAE, CBE, CCE, CDE. So same concept. Macam cari CA, CB, CC, CD. Kita tahu Ca0, kita tahu X. You can already find the concentration of all these compounds. So this example shows you how we express Kc. Okay, in this case, so you can see we have two product, B and C. So concentration of B at equilibrium multiply with concentration of C at equilibrium, power of 2, because the stoichiometric coefficient of C is 2, stoichiometric coefficient of B is 1, over concentration of A at equilibrium, power of 2, because the stoichiometric coefficient is also 2. Okay, so now you get the correlation. So now we replace pula. Okay, CBE equals to B per A, Ca0 Xe. C, concentration of C at equilibrium will be C per A, Ca0 Xe, but we have to power of 2 because it's power of 2. And we do subsequently for A. Okay, Ca0 in bracket 1 minus Xe, close bracket, power of 2. So in this case, we are assuming this is liquid phase, kan? Okay, so I should write clearly this is liquid phase lah. Sebab kalau gas phase, dia dah tak macam ni, right? So this note I should add, saya tulis ni liquid phase. Okay, right, sorry. I didn't realize, I've written here clearly liquid phase. Sebab tu kita boleh express macam ni. Okay, alright. So again, alright, katakanlah if you find this is quite hard to compute or hard to see how it's being practiced, always remember that dalam calculation, it will have numbers. So when you have numbers, it makes more sense to the equation. So now if you see in variables, you might find it a bit difficult, but later on when we have numbers, you can see it's easier for you to understand. Okay, so done. Now kita dah tahu Kc. So again, to repeat why you need to know Kc, most of because in the rate law for reversible tu akan ada Kc. So kami ingatkan dalam design equation kena ada rate law kan. Kalau tak ada rate law kita tak boleh cari the design of the reactor. So rate law dia pula ada Kc. So sometimes you have to find Kc first, or sometimes from the Kc value kita cari conversion, ada equilibrium conversion. Okay, so how now to do the rate law kalau ada reversible reaction? So reversible reaction pun the same concept as irreversible, dia ada elementary rate law, non-elementary rate law. So for those yang baru tutorial tadi, I think you can clearly understand, remember, rate law ni ada dua jenis kan, elementary, non-elementary. So kalau non-elementary, the rate law will be given to you. So let's say sebab rate law dia, reaction order dia dah tak follow the stoichiometric coefficient. So the information has to be given. Kalau elementary, Zulfaqar tak tutup mic ke? Ada soalan ke? Zulfaqar? Yes. Okay, kalau kamu nak tanya soalan, kamu raise hand sebab sekarang saya tak pasti kalau mic tu terbuka. I'm not sure whether you accidentally or what. If you have question, you can raise your hand. Okay, right. So kalau this is elementary reaction, okay, kamu ingat kan kalau elementary, irreversible. Again, elementary irreversible yang sebelum kita buat, kita akan ikut stoichiometric coefficient kan kalau dia elementary irreversible. What about elementary reversible? So kalau elementary reversible reaction, meaning the reaction obeys elementary rate law for reversible reaction, dia ada rate law dia yang special. Okay, again, kalau dia nak elementary, information tu akan diberi kepada kamu. So kamu follow je ni. Dia punya questions, what is the information given. But if they mention elementary, reversible elementary rate law dia ada special design of it. So this is the part that you have to understand how to relate or how to write down the rate law. Okay, so the rate law is given as minus RA, sama je lah kan minus RA, tapi macam mana rate law dia? So rate law dia equals to, first of all, K sama, reversible, irreversible, depan tu mesti ada K dan K dia must be at the reaction temperature regardless. Kalau dia at 350, the K must be at 350. Regardless irreversible, reversible, konsep K masih sama, dia mesti pada suhu tindak balas. Okay. The part yang susah dalam bracket tu. So dalam bracket, it will equals to, the first one will be the concentration of your reactant on your left hand side, power stoichiometric coefficient. So contoh dalam case ni, I have 1A reversible to produce 1B, right? Okay, ataupun other way round, it will be concentration of A power stoichiometric coefficient. I only have one reactant. Okay, minus the next part of the bracket will be the concentration of your product. In this case, we have B. Okay, so it will be concentration of B power stoichiometric coefficient dia. Okay, but now it's per kc. So tu tadi saya kata kita kena cari kc sebab dalam rate law reversible tu akan ada kc. So we have to find the correlation because we need to find the kc so that we can replace in this rate law. Okay. So again, this rate law is not provided to you. Sama macam irreversible. I cannot provide to you this rate law. Why? Because naturally you understand rate law ni tak fix, right? It depends on the reaction. Macam tindak balas ni, saya ada satu kiri, satu kanan. Tak apalah. Let's say sekarang kalau saya berubah di mana saya ada A and B on the left hand side, C and D on the right hand side. Maksudnya A and B reversible untuk menghasilkan C dan D dan dia ada way and the backwards. Okay, so rate law dia akan menjadi minus RA equals to K masih sama. Dalam bracket sekarang kita akan ambil kira concentration of the reactants. Okay, again, I must repeat. Mungkin kamu confused kan, saya cakap reactant produk tapi dia tindak balas berbalik kan. So sebab tu kamu kena faham. Kalau tindak balas tak berbalik, kita biasa buat rate law berdasarkan reactant sahaja kan. Tapi kalau kamu tengok sini sekarang, rate law ni yang bahagian belakang tu kita dah ambil kira produk. Kenapa? Sebab dia berbalik. Just that when we talk about reactant product tu, we talk conventionally sebab kita dah selalu faham yang kiri tu reactant, yang kanan tu produk. Okay, tapi reversible kamu kena faham yang produk tu pun boleh menjadi reactant balik. Sebab tu rate law dia bahagian belakang tu dah masuk concentration of the product, which we do not do kalau dia adalah irreversible reaction. So that's why the rate law katakan sekarang saya ada dua reactant, dua produk. Okay, so it become K is still there, but now you see in the bracket, the first part will be the concentration of your reactant. Case ni ada dua dah reactant. So kamu tengok dalam case ni B adalah reactant, B muncul di bahagian depan. Tapi the previous example, B was the product, right? Kamu tengok bila B adalah produk, B muncul di belakang. Sebab tu equation ni cannot be provided. And contoh sebelumnya tak ada C and D. Contoh ni dah ada C and D pula. Sebab reaction ni saya menghasilkan juga compound C and D. Okay, so it become CA, CB power of the stoichiometric coefficient minus K minus the second bracket will be the concentration of your C and D power stoichiometric coefficient divided by Kc. So Kc is equilibrium constant, K is reaction rate constant. So this part you cannot get confused lah daripada information dia. So now we have already found out how to find Kc, the correlation. You already find out juga how to do the rate law. So yang penting kamu kena faham how to form the rate law, and I think the main challenge will be bila kamu nak express concentration dia, sebab kamu ada concentration liquid dengan gas. So we will discuss in the next example. Right, okay, so this slide is just to show you macam mana kita nanti nak combine untuk design reactor. So ingatkan bila kita nak elucidate equation dalam chapter 4, always tell you we must have that three criteria, right? The type of reactor, rate law, and the phase. Okay, so kalau kamu ingat untuk batch dengan PFR, design equation dia ada pengamiran, right? You got the integration. So imagine kalau nak buat integration of this rate law is very difficult. Boleh, I do not say it's impossible, but it's very difficult for you to derive. If you remember, I derive for you batch dengan PFR untuk irreversible pun equation dah panjang sebab dia melibatkan pengamiran. Okay, so what happened is, okay, to make it simpler for you, we will just learn if we want to design reversible CSTR reaction. Okay, again, doesn't mean yang tak mungkin reversible guna batch, reversible guna PFR. Ada je, just that the calculation will be complex, the equation will be too complex for you, it's very hard for us to derive the equation. So kita buat yang sedang saja, kita buat untuk CSTR sebab CSTR doesn't have any integration. Dia just a simple equation sahaja. If you remember, design equation dia linear kan? Volume CSTR sama dengan FA0 per minus RA. So minus RA itu sekarang dah berubah rate law dia sebab kita sekarang reversible reaction. And then jangan lupa kita ada CA, CB tu. So CA dengan CB tu kita kena kira, kita kena express pula. Nak cari CA, nak cari CB. And you must remember the CA and CB akan berubah kalau ada liquid, ada gas. Okay. Now again, satu benda yang sometimes student may get confused. Kenapa dalam rate law kita guna CA, CB. Kita tak guna CAE, CBE. Okay. So if you remember, I taught you, kalau at equilibrium, okay, dia punya tindak balas dia kan saya dah kata dia macam kesimbangan, di mana tindak balas the minus RA is actually 0. Sebab kepekatan A, B, C dan D dah sama. So rate law dia punya rate of reaction adalah 0. So kita takkan design reactors based on the concentration when they have already achieved equilibrium. Kita takkan design reaktor berdasarkan kepekatan yang mana masa dia dah capai equilibrium. Sebab kalau dah capai equilibrium, minus RA itu dah kosong. Dah tak adalah design reaktor tu, dah tak ada volume dah sebenarnya. Pengiraan dia sebab minus RA itu kosong. So what happen is, we will always design the reactor based on the concentration or based on the reaction sebelum dia capai keseimbangan. Okay, contohnya katakanlah, if the reaction takes you 1 hour to achieve the equilibrium conversion of, let's say, 80%. Kamu kena ingat kalau reversible reaction, the highest conversion they can achieve is their equilibrium conversion. Dia dah bukan 100%, dia adalah equilibrium conversion. So katakan dalam masa sejam, dia dah mencapai keseimbangan, katakan the equilibrium conversion is XE itu adalah 80%. Unless you disturb the system, it can never go above 80% of the equilibrium conversion. So that XE akan memberikan kamu CAE, CBE, CCE, CDE, right? We will not use that concentration or we will not design our reactor based on bila reaction tu dah capai keseimbangan. We will run it and design it so that it will only run before it achieve the equilibrium conversion. Sebab tu dia akan menjadi CA, CB, CC, CD dan X. Sebab kita akan measure that concentration before the reaction achieve equilibrium. So katakan kita tahu reaction tu 1 jam capai keseimbangan, kita akan design supaya reactor tu akan, the reaction only akan habis ataupun we will get the product before the reaction finish before the reaction at 1 hour. Before 1 hour tu kita dah ambil keluar produk sebab kita tak nak reaction tu mencapai keseimbangan. So you can understand why ada CAE, CBE, CCE, CDE, kita guna tu untuk kira KC. KC kena kira pada keseimbangan sebab KC tu equilibrium constant. So kenapa kena kira KC? Sebab KC ada dalam rate law. Okay, tapi bila kita nak kira rate law dia, CA, CB ni takkan menggunakan equilibrium punya concentration. Okay, so hopefully you understand that part. Nanti dalam soalan, you get a bit confused. Kejap kira equilibrium, kejap kira bukan equilibrium. So I have to explain that first. Later you see example what that it means. Okay, so this slide pula tunjuk slide pertama, slide kedua just menunjukkan beza kalau saya ada different types of reaction, what happens, apa yang akan berubah. So kamu just kena ingat, I have different type of reaction, yang berubah adalah rate law dia kan, sebab tadi satu A, satu B, A menghasilkan B. Nah ni A dan B menghasilkan C dan D. So rate law dah berubah. Okay, again kita kena express concentration dia. So tak semestinya hanya A, B, C, D. Mungkin jadi A, B menghasilkan C, maybe A menghasilkan B and C, so on and so forth. So I give you the example, but again, must remember it will change according to the types of reaction. Okay, so let us try one example for you to understand better. Okay, right. So they say the liquid phase isomerization reaction is given as following. 2A to produce 1B. Okay, so reversible lah. Mula-mula 2A tu menghasilkan B, dan reversible B menghasilkan E. Okay, the reversible reaction carry out in an isothermal constant pressure flow system. Okay, so ni adalah liquid phase, and then liquid ni pula isothermal, tak ada perubahan suhu, tak ada perubahan tekanan. So this is a good thing. No pressure change, no temperature change with pure A. So YA naught adalah 1. Okay, and with at initial concentration of 0.7, so your CA naught 0.7. Okay, and then flow rate of 30 liter per second. So epsilon naught 30 liter per second. CA naught 0.7, epsilon naught 30 liter per second. Given reaction rate constant K 1110, equilibrium constant KC 0.8. Okay, so that kamu kena make sure you really understand what is K, what is KC. KC adalah pemalar kadar tindak balas pada equilibrium. K adalah pemalar kadar tindak balas. So you must know the difference lah, right? So they say determine the equilibrium conversion XE. So ingat beza dia XE dengan X. X adalah conversion sebelum mencapai keseimbangan, and kita akan design reactor pada conversion sebelum keseimbangan. So maksudnya pada X, bukan XE. Contohnya katakan XE saya 80%, saya akan design reaktor saya let's say pada 75% or 70%. Kita tak nak dia dah mencapai keseimbangan. Sebab pada keseimbangan, kadar tindak balas itu adalah kosong. Tak boleh, right? Okay, then so kita kira XE and subsequently calculate the volume of CSTR. Okay, if given the reactant A conversion in the reactor is 90% of the equilibrium conversion. Okay, so again, for mini project stage 2, okay, as just now I mentioned for the tutorial, I also mentioned today, it's mentioned in this lecture, saya dah keluar kalender untuk deadline untuk mini project dalam week 12. So since you don't have lab, probably this week, and I heard probably next week pun mungkin takkan ada, I'm not sure. Please use the time untuk buat mini project. Sebab mini project sebenarnya tak susah and you can complete it fast. Sebab later on nanti bila dah ada lab, kamu dah kena fokus lagi do lab report, kamu ada lagi test, kamu lagi banyak lagi assessment subjek lain. So if you have time now, take opportunity, you got no lab, to complete your mini project stage 2. Mini project stage 2 tu tak susah, very easy because it's just calculation. So if you really focus, half a day you can actually complete already yang stage 2. Okay, so stage 2 week 12 already give you the deadline. I don't think there's any more extensions sebab lepas tu lagi banyak lagi deadline yang kamu kena buat, right? Okay, come back to here. So why I mentioned about mini project, sebab dalam mini project tu nanti sometimes student will get confused about conversion. Okay, so kamu kena faham, when we talk about conversion, walaupun kalau kamu ada satu reaktan ke, ada dua reaktan ke, conversion tu akan berdasarkan satu reaktan sahaja, satu compound sahaja. Sebab tu saya kata, bila kita ada tindak balas, kita kena tahu conversion tu berdasarkan yang compound mana. Compound tu akan menjadi compound A kita. So, if you kata, let's say you have sodium hydroxide at acetate. So, kalau kamu kira conversion berdasarkan sodium hydroxide tu jadi A kamu lah. Okay, so macam bila kita buat conversion, kamu kena betul-betul know the conversion is based on which reactor. So for this example, dia kata conversion, kita kira volume reactor. Kalau conversion reactant A saya adalah 90% of the equilibrium conversion. So remember I told you, kita design reactor, kita takkan guna equilibrium conversion. Kita akan guna pada conversion sebelum dia mencapai equilibrium. So dalam soalan ni, kita kena tahu dahulu what's the equilibrium conversion. Sebab kita kena make sure reaktor kita tak mesti pada conversion yang mana dia belum mencapai equilibrium. So soalan ni kata, you find first Xe and then you design your reactor of which conversion dia 90% of your equilibrium conversion. Maksudnya katakanlah equilibrium conversion, bila kamu kira equilibrium conversion kamu, let's say 80%, 0.8. So Xe 0.8, but your X will be 90% of that 0.8. So kamu darablah 0.9 times 0.8, that will be your X. Okay, again, what is the difference between X and Xe? Xe is the conversion when the reaction achieve equilibrium, but we will not use that equilibrium conversion in our reactor design. We will use at certain percentage before it reach equilibrium. So dalam soalan ni dia specify, dia mesti 90% daripada equilibrium conversion. So kalau equilibrium conversion saya 0.8, 80%, my reactor conversion will be 90%, let's say, of the 0.8. So 0.9 darab 0.8, atau 0.72. So reactor saya punya conversion adalah 0.72, which is lower than the equilibrium conversion. Okay, so solution part 1. Macam mana kita nak cari equilibrium conversion? So that's the challenge dalam soalan ni. Kalau tak tahu equilibrium conversion, takkan tahu reactor conversion. So how do we find equilibrium conversion? The only thing yang ada perkataan equilibrium dalam soalan ni adalah equilibrium constant. So dia beri kita equilibrium constant. So by right, from the equilibrium constant, we can find the equilibrium conversion. So macam mana kita nak cari? Okay, so if you remember, I already taught you equilibrium constant Kc equals to concentration of your product, power stoichiometric coefficient, over concentration of A, power stoichiometric coefficient there. So in this case, Kc will be equals to concentration of B at equilibrium per concentration of A at equilibrium power of 2, because the reaction is 2A. So from this first part, you may wonder, tapi tak ada lagi X, right? Sebab tu kita kena express pula CAE, CBE in the form of CA0 and Xe. But before you want to express, you have to remember ni gas ke liquid. So this is liquid. Okay, so kamu somewhat, you have to remember how to express the concentration. So expression concentration ni tak diberi, kamu kena tahu sendiri. Tapi tak apa, I understand at this moment you have a lot to digest. Okay, that's why I will tell you which one is important, and then towards the test and towards the exam, I will again tell you what is you need to know, basis for you to focus on exam and test. Tapi at this moment, you kena faham dulu konsep dia. Sebab tu bila saya beritahu masa exam dan test tu, kamu dah terus tahu apa sebenarnya yang penting. Okay, so kita kena express dulu concentration dia. So kalau kamu ingat, kalau kita ada liquid phase flow system, says they are flow, right? So liquid phase flow system, CAE akan equals to CA0 in bracket 1 minus Xe. Jadi kalau kita sebelum ni kita buat CA, right? CA equals to CA0 1 minus X. So kalau CAE, beza dia CA0 masih sama, just that X tu sekarang menjadi X equilibrium. So you may ask, tapi kenapa kes ni kena Xe? Sebab kita nak cari equilibrium constant, equilibrium conversion menggunakan equilibrium constant. Equilibrium constant kan semua benda mesti pada equilibrium. Okay, so then I get from the question CA0 is 0.7, Xe I want to find. So similarly, I have to do for CBE as well. So CBE is expressed as B per A, CA naught XE. Okay, you have to somewhat remember in chapter 3, we learned to express concentration. So, chapter 3 tu, I taught you how to express concentration, but you don't really use it. Now you are using it, but now dalam form equilibrium, dalam form reversible reaction. So then you replace, you will get as CBE as 0.35 XE. So XE itu kita biarkan. We replace into the equation sebab KC kita tahu. KC kita tahu. CA naught kita tahu. The only thing that we do not know is XE. So naturally, if you solve this is again quadratic equation, you will get your XE as 0.4014. So now I know that I can, my reactor conversion tak boleh lebih ataupun sama dengan 0.4014. Conversion yang saya nak dalam reaktor saya tu mesti kurang daripada 0.4014. So subsequently, I can now solve the second part because saya dah tahu dah kalau equilibrium conversion saya 0.4014 and the reactor conversion dalam soalan dah kata mesti 90% of the equilibrium conversion. Means my reactor conversion X sama dengan 0.9 XE. So saya dah tahu XE saya 0.4014. Replace, I will get my reactor conversion saya sekarang 0.3613. So you see, equilibrium conversion 0.4 tapi design conversion reactor saya yang saya akan design hanya akan mencapai 0.3613. So now I want to find the volume, right? Okay, so nak mencari volume dia, kalau kamu tengok di bawah, I go to the down first. Kita faham design equation dahulu. Volume CSDR sama dengan FA naught X per minus RA, one single reactor. So FA naught X per minus RA. We do not know FA naught, but we know CA naught dan epsilon naught. So I can replace it in the form of CA naught multiplied with epsilon naught X per minus RA. Okay, so this part, you have few options. Okay, you can actually terus ganti masuk dalam minus RA tu equation rate law yang panjang, ganti-ganti masuk dalam, but it becomes a bit complicated. So in this case, what you do is you can first find out first nilai rate law tu, minus RA tu dulu. Dah dapat minus RA, baru ganti ke dalam equation ni pun boleh. Okay, so let's say we do this step. Kita cari dulu nilai minus RA. Okay, so kita tahu this is elementary reaction. Again, you must remember rate law ni hanya valid kalau dia adalah elementary rate law. Reversible elementary rate law. Kalau dia tak kata, dia kata non-elementary, this rate law is not valid anymore. I have to give you the information. So let's say dia kata this is elementary rate law. So minus RA equals to K. In bracket, K is reaction rate constant. In bracket, concentration of your A, of your reactant, power of 2, minus concentration of your product, B, technically power of 1 sebab 1B over KC. Okay, so kita check dulu one by one untuk minus RA. So the K is 1110. Okay, CA. Okay, so you have option of cari dulu CA. Okay, dalam case ni you can do step by step. Why not kita cari dulu CA? You can also replace dalam equation panjang-panjang dalam rate law, tapi you may have the tendency to do mistakes. Why not we find first CA? So kita carilah CA sama dengan CA naught in bracket 1 minus X. Tadi ingatkan, tadi kamu cari CAE. So jadi CA naught in bracket 1 minus XE. Yang case tu bila kita nak cari dalam case KC. Dalam case sekarang dalam design reactor, kita kena based on the conversion yang kita dah tadi kira, which is 0.3613, which is our X. So itu kita ganti dengan X yang kita dah decide, you get your CA. You do the same for CB. Okay, so I hope you don't get confused. Tadi yang kita buat tu adalah untuk cari XE pada equilibrium. Sekarang kita nak design reactor, kita dah ada conversion reactor kita sendiri. Kita guna reactor conversion tu untuk mencari CA dan CB kita. So when you have the CA and CB, then only you replace into the rate law, okay, minus CB per KC, KC 0.8. So now you get your minus RA punya value. So minus RA punya value, you replace into the final equation. Now you get the volume of your CSDR. So this is the stages punya calculation. Okay, so again, this is just optional. You can also terus ganti masuk equation tu combine baru kira pun boleh, tapi this is a easier way lah. You kira one by one baru you ganti masuk. Okay, right. So last one, I have one more example. Not example, this is actually our tutorial question number 6. Okay, so that since we just finished the notes, we just finished the lecture, I just add one more question tutorial number 6. So means that dalam tutorial saya dah tak cover lah soalan ni. So saya dah cover dalam lecture. So let's say we try another question. Okay, so the question says, the production of B is carried out in an elementary reversible reaction in a flow reactor. So sekarang reaction dia A menghasilkan B tambah C. So kamu tahu kan kalau reaction dia dah berubah, rate law dia pun dah berubah, nak cari Kc pun dah berubah. And dia kata 90 mole percent reactant A at an initial concentration of 5 mole per liter with the remainder inert in the gas phase is fed to the system at the pressure of 5 atm. So kamu boleh tengok dah soalan ni soalan yang slightly more difficult. So first thing kata, walaupun reaktor saya adalah A tapi dia bukan pure A. Asalnya dia ada 90 mole percent A and 10 mole percent inert. Maksudnya YA naught dia 0.9, YI naught dia 0.1. Okay, so you must be very careful. Although sometimes I may have only one reactant, not necessarily is 100 mole percent of that reactant. You may have impurities, you may have inert. Okay, next one, Ca0 5 mole per liter, and dia adalah gas phase, so elementary gas phase, and fed to the system pressure P0 dia adalah 5 atm. Okay. The reaction rate constant is 500, K is 500, equilibrium constant is 0.5, Kc 0.5. There is a pressure drop to 3 atm after the reaction. So sekarang ni lagi mencabar dari gas phase, ada pula pressure drop. So berapa pressure drop dia? Asal P0 is 5, tapi selepas tindak balas, P dia adalah 3. So dia kata pressure drop to 3 atm. So maksudnya P0 is 5, my P is 3 atm. Okay, right? So tadi yang, for those yang dah buat tutorial tadi, in the example that I discussed just now, it was a pressure drop of 2 atm. So sekarang kamu tengok contoh ni, pressure drop to 3 atm. So kamu kena faham perbezaan dia. Okay, yang satu lagi section tutorial tak apa, later I will explain to you during the tutorial session on Thursday why this sentence is very important for you to differentiate the difference. Either pressure drop to atau pressure drop off. Apa beza dia, okay? So then, they ask us to determine the equilibrium conversion. So sama macam contoh tadi, they ask us to find Xe and subsequently, again, calculate the volume of CSTR di mana the given conversion must be 80% of the equilibrium conversion. So sekarang soalan ni pula, soalan kedua dia punya conversion dalam reaktor kita tu mestilah 80% daripada equilibrium conversion kita. Sebab tu part A kena tahu dulu equilibrium conversion. Baru kita boleh specify berapa persen daripada equilibrium conversion itu akan menjadi conversion reaktor kita. Okay, so this question is tough because kamu dah kena tengok kenapa dia beza. Okay, first of all, cari case dia pun dah berlainan lah kan, sebab tadi case tadi ada satu A menghasilkan B. Case ni ada satu A dan ada B dan C. So kamu punya equilibrium nak mencari Kc tu pun dah lain. Pengatas dia will be concentration of B at equilibrium, CBE multiply with concentration of C at equilibrium per concentration of A at equilibrium. Tu satu benda yang berbeza. Benda kedua, kita nak express concentration dia. Kita dah express berlainan kan, sebab sekarang dia adalah gas phase with pressure drop. So kamu kena ingat macam mana apa berlaku, what happens to the concentration yang kita nak express kalau dia adalah gas phase dengan pressure drop. So kalau tadi CAE equals CA0 in bracket 1 minus Xe, kalau kamu ingat tadi liquid phase. Sekarang kalau gas phase with pressure drop, beza dia ada pembawa 1 plus epsilon Xe dan ada yang sebelah kanannya ada P per P0, the pressure drop. Okay, so you can't remember this, you have to check back lah bagaimana kita nak express this concentration dalam chapter 3 kalau ada kes yang ada perubahan tekanan. Okay, so the same for B, same for C, you have to calculate the concentration at equilibrium. Okay, you have to solve this quadratic again in order for you to get the equilibrium conversion. So normally soalan macam ni, final exam, I will come up something like this. Sebab tu I get you familiarized first, but before later on when we come to the final exam, I will again explain again lah for you to remember. But this is among the hardest equation yang kamu kena solve. Because you have quadratic, you have layer 1, layer 2, layer 3, layer 4. Okay, and subsequently after you dah tahu the equilibrium conversion, so buat balik lah, kita kira balik the reactor volume pada conversion di mana dia adalah 80% daripada kamu punya equilibrium conversion. So kamu tahu equilibrium conversion, kamu darab dengan 80% of it, you get the reactor conversion as 0.3. So you do the same. You find back CA, you find back CB, you find back CC. You calculate the minus RA based on the reversible rate law. Then you replace into the design equation, you will get the volume of the CSTR. So normally question untuk reversible ni dia tak lari jauh lah, dia macam ni je. Sama ada dia akan first cari reversible punya equilibrium conversion, then cari volume of the CSTR. Just that beza dia, adakah dia liquid, ataukah dia gas, adakah ada pressure drop ke, tak ada pressure drop. That's the only difference in the question, so that you have to understand how it changes when we have that kind of situation. Right, so I finished today for chapter 4 lecture. So again, for those yang saya tak announce lagi, besok we got no lab. Okay, we still have no water, so there's no lab tomorrow. I will continue the tutorial for T1 as well as the lecture for the rest on Thursday, where we will proceed with chapter 5. Okay, so you have no question. That's all for today. Thank you very much. See you guys on Thursday. Right.